Hello, I'm Michał, and today I will tell you about my little side project that I did over the Christmas and where I learned about ePDF and the Go. And yeah, so what kind of triggered me to think about this project? So some time ago, there was this Shape-Loot attack where through some infected NPM packages, attackers were running the truffle hog. This is a program to look for some secrets, like in .env files or like AWS credentials, GitHub tokens, stuff like this. And the script would run, find all the important credentials on your machine, and then exfiltrate them to GitHub later for the attackers to get. And then I thought like, like I do also some JavaScript in my computer, and I would rather like not be not have this problem that all of my important credentials are exfiltrated. And I started to look. Maybe there was like a good solution for it, something very easy, but there was not. And so I thought, okay, I would just try something myself and maybe take it like with a small grain of salt. I'm like not like a professional security guy. And actually, I did not really check if it helps against this attack, but it was it was a super nice side project where I learned quite a lot, and I'm very happy to share all my learnings. So my idea was that we will observe all the calls to open files, because like if you are scanning the files, you have to open them, and I thought that you can create a list of some important files on your computer, like this GitHub credentials, AWS credentials, maybe your like a crypto wallet, passphrases, stuff like this. And I'm pretty sure like you can create such a list. And then I thought, okay, so maybe let's do something, let's say simple at the very beginning, and check if those files were opened like at least 2 times by the same process, like 2 different important files by the same process. And this is probably something very suspicious. And then I learned that, there's this ePDF thing. And this is a technology. This is like a Linux technology that allows us to run like a sandbox programs that run inside of the kernel. You have some things to which you hook, and then you can get some data. You can modify the behavior of the syscalls, monitor network, stuff like this. And this whole stuff is created in such a way that it's safe. But even if you write something very stupid in your code, it will not crash the kernel. And the cool thing is that you just compile it once, and you don't have to recompile it with every kernel version. I'm pretty sure that whoever used Linux went through this pain of reinstalling some modules for, I don't know, NVIDIA or something with every update. So this is a cool thing with this technology. It's not necessarily compiled once and run it everywhere. And this is how it kind of looks like. The core of our program, the whole kind of, let's say, business logic is here in this Go library. And to kind of connect it to the kernel, we would have to write some C code. This is this part here, where we create C files, and they get compiled to the bytecode, but then it gets interpreted by the kernel. And there's a way of communicating between, there's like a very clear interfaces to communicate between our Go library or like a Go program and the kernel itself, and we'll just explore them. And today there will be some C on the screen as well. I will try to keep it minimum and focus mostly on the communication and the other important things. There's this nice little project, eBPF Go, that we'll be using today. It's open source. It's pretty mature, very good tooling. I think if you would like to start with eBPF, this is the right place for it. And so kind of the first step, how I will be going, how I kind of progress with this program. I started with something very, very simple. So how to kind of block one process from opening a file, just something like this, without any smart logic of checking how many restricted files were there, just to see if it even works. So we'll start with some C. Oh, this is a funny thing that every single eBPF program has to be GPL licensed. Like otherwise, if you don't have the header there, it will not run. I found like a very interesting. The next bit. So this is how we define the communication channel between our C program and the Go program. This is a thing called maps, and we create our map called block PIDs. And first we define the type of it. It's like a hash map. And we say what's the maximum capacity of it. And then we create like it's a hash map, right? So the key is of type uint unsigned integer, like a 32 bits, and the value is 8-bit unsigned integer to keep like a 1 and zeros. Then we say like to which syscall do we want to hook. Here we say for every file open. And and just not to really get very deep into it, from this eBPF libraries, we are able to get the PIDs. And I might have just go a bit back. The important bit here is that first of all, we do some like a little logging that we can later see in like an eBPF console. And the important bit is that if the file is blocked, I mean if the PID is blocked from opening, every subsequent call to open the file will result in a permission denied.
So the blocked is a pointer there, and so line 28 checks whether blocked is nil, right?
Yes.
Yeah.
Yeah, exactly. So if it's not blocked, right, we are okay, right?
The comment at line 16 says one is blocked.
Yeah. So that's why I say, like, if it's not blocked, right? We say we are going to 0, right? So return 0, because if it's not there or it's 0, right? We are coming here and return like okay, return 0, right? And in all the other cases, we return permission denied.
I suspect if the map contains an entry with the value 0,
yes,
then it will be detected as blocked.
Might be. I mean, yeah, as I said, I just don't want to focus very much on the. See, yeah, you are very likely. Yeah, it's a Go Meetup.
More terrifying because he's
Yeah.
sitting in the chair, you know. It's like
Yeah.
hat is missing.
This one carries the
It was not PID. It was it was the blocked. It was the value there.
zeros. Yeah. No zeros in the maps.
Yeah. Yeah, I think you're right. I might have missed it. I was just removing, but you're indeed true. That might be Matmo was not the right structure there. So next we have just this like a nice Go generate block that uses this BPF to go and generates us some files. Here we have this C file that contains the logic I just showed you the moment before. And there's a bit of a funny thing that, okay, I didn't know it, but with Go, you can also compile like a C files, and it's quite important to keep them in the, like keep all those BPF files in the separate directory so you don't have to fight with the build. And yeah, after the running it, we get 2 files. One for big endian, the other for the little endian machines, and the whole the eBPF Go is able to check on which architecture is it running and import the right one. And inside of all of those files, we have BPF objects. So there we have programs. In our case, it's deny file open, and this is the annotation for it, how it's called, right? And also the map that we defined. And yeah, this is the Go code that we would import and use. So how do we use it? First maybe the imports, right? Everything is this Cilium eBPF, and then we have to load the objects, where we point the objects from this file that we created, and then we attach LSM. It's a Linux security module. This is we'll see also the other way. I mean the other hook that we attach, and we say that this is LSM. If you maybe remember, I will not go like a couple of slides back, but there was this LSM/file open, and this is why it's so, because this way we are able to modify the behavior of the system call. Yeah, we just load it like this, and then to have this communication, we have to update the map. I mean, we have this block PIDs. The map, it comes with this update method, right, where we put the PID that we want and this value of 1, and this will be nicely interpreted by this C code that you saw a bit before. And yeah, for these maps, yeah, there are hashes, arrays, queues, circle buffers. There's like a lot of them for many different use cases that you can probably imagine. And yeah, I will not go through all of them. If you are just curious, yeah, you can you can check it themselves. Yeah. So coming back, right, we have the C code that using CLang gets compiled to this program. We also have some maps defined there, and then inside of our Go library, we call things from this program and read and put things. In our case, we are just putting things to the map for the eBPF to read from. But like soon, I will show you how to read from those maps as well. And then eBPF handles all those like syscalls hooking for us. Yeah. So now let's go to the second bit of it. We'll check. I mean, we'll be reading from some messages sent by eBPF and handling them. So first, let's start with defining the event. We'll be putting all the opened files in our system in something like this. So we have the PID that opened it, who opened it, like which user, the name of the command for nice logging, and the file path. We also have all the flags, like was it for reading or writing. We can later do something about it. And then as a next step, we defined a ring buffer. So we'll be writing always to it, and then the Go program will be reading out of it, like taking things out. And in case we are too slow in Go program, like the content will be overwritten. So like no slowdown for the kernel, but we might miss something. But I thought, yeah, it is okay for this case. And again, we call this map events, and yeah, some size. This is the only thing that we have to define there because it's just bytes. This is a bit maybe of an issue. It's not really typed. And here, so beforehand, we were hooking into LSM file open, right? And here we have another type, trace point, and it's hooked to this sys enter opened. And there are different hooks, and also, unfortunately, for different Linux versions, some of them are variable, some of them not. So it's not perfect. I just used here the version 2 because it's like a less code. The version 1 is a bit more verbose. I think this is why they created a version 2 to make it less verbose. And they're very similarly to what we had in the previous example. We are doing something with our map. In this case, we have this nice little helper submit. I mean, beforehand, we built this event, right? And then we submit to our ring buffer for our Go program to be read. And this is like, we have a couple of trace points. I will maybe go later with like a more extensive list of them. But we have trace points where we have like access to things happening in our system, and LSM, Linux security modules, where we can modify the behavior, like deny something, change what is opened, or stuff like this. With trace points, it's really like showing, watching what is happening in our system. And now there's this little thing that I kind of did not like is that this event structure you have to redefine yourself in Go. There's no automated way of kind of transferring those interfaces. So we have to be careful with the changes on both sides. And yeah, oh, sorry. Then you just read it like using a normal reader. And then, yeah, like a binary read, right? We say like a new reader, and we just read from this ring buffer. I think I did not put exactly the opening of the ring buffer, for which I'm sorry. I will point it maybe later in the comment. But the idea is very similar. We just read from it, and this way we get the access to these events created in eBPF. And this might get a little bit like difficult. You cannot really put debugger in your eBPF code to look what is happening, and sometimes it's quite difficult to follow. So in the newer kernels, the kernels that support eBPF have this BPF tool, and with it we can first of all see all the maps, right? And their first map is this PIDs that we defined before, and the second one is this ring buffer, right? PIDs of the type hash map, blocked PIDs of the type hash map, right? And the ring buffer of the type events. How many? Like how big is it? What's inside? And we can even inspect what is exactly inside, which I find like a super nice for debugging when you don't know if you just wrote your C code wrong, but it doesn't block the opens, or it is the Go part that is missing something for the communication. It yeah, as you can see, it works nicely with the JSON format, very readable. You can also, I think, write to the maps, and yeah, the BPF tool is really helpful thing if you would be doing this eBPF stuff. And we can take a look at some other trace points. Yeah, so I thought about security models. We can get some probes, some traffic control for the networking, C groups, also work on the sockets themselves. There's like a plenty of things to which you can hook and do things, and yeah, build your stuff. From what I saw, quite a lot of things that are using eBPF and are written in Go are like network-related things, where you can observe and maybe do some routing. Yeah, so you can use eBPF to safely interact with the kernel. It's just like a bit of a C code, and the rest is nicely handled in your Go application. And yeah, you communicate with the maps that you can debug using BPF tool. And yeah, the nice thing is that you can like keep the C part very minimum and use the Go to handle this like a nice business logic. And I was not sure how fast it will be, so maybe I will show you some very prominent eBPF project. I think the Cilium is the first one, I think the biggest when it comes to the stars on GitHub. And yeah, it's like a network observability tool written in Go. Apart from it, yeah, Pyroscope from Grafana, also mostly observability. And yeah, there is this eCapture when you can check, like read some stuff from SSL TLS connection, because it's working on the kernel level, so everything is already decrypted nicely for you. And like, of course, you cannot miss like a Kubernetes things with Go, right? So there's also a platform for security using eBPF that uses Go. And this will be the last slide I prepared for you today. And if you have any questions, I'll be glad to answer them.